I don't know which one. Let me see. This one? Yeah. Okay, thank you. Okay. Thanks to the organization for the invitation to talk about my work. And today I will talk about the zero-range ultracold fermi gas along the BCS and BEC crossover. Well, first of all, previous theoretical studies were performed with finite range potentials that required extrapolations to the zero range. Typically, in Monte Carlo simulations, they use a specific energy potential in the Hamiltonian. Then they normally have to do an extrapolation to take the zero range limit. In this work, zero range potential is used to investigate the equation of state of an unpolarized ultracold fermi gas in the BCS-BEC crossover with no extrapolation. To do that, we apply the Wigner-Bethe-Peters boundary condition in our calculations. We put this condition in the wave function of the system. And we calculate the radial distribution functions of unlike spin pairs and the contact parameter and per unit of volume for several values of the scatter length in this range. And fitting the radial distribution function, we can obtain the contact parameters for different values of scatter length. Okay. The effects of zero-range potential are taken into account using this condition, that the wave function goes to 1 over r minus 1 over the scatter length when the distance between two particles with different spins goes to 0. If you consider this condition properly, the Schrödinger equation you have to solve is like this. Then you have to use just the kinetic energy terms in your Hamiltonian. Well, the wave function model used to describe the system must be antisymmetric, and it's given by expression. And psi t has essentially two terms. The first term are the Jastrow term that correlates the interaction between particles with different spins. And the BCS term is written like this, where the A is the operator of antisymmetric the particles with the same spin. Well, phi is the spin orbital that we consider like an expansion of plane waves, where the set of alpha j are variational parameters associated with different shells with moment kj. Then we can optimize the set of alpha j, and this BCS part of the wave function defines the surface of nodes of the wave function, and in the diffusion Monte Carlo calculation, we consider the fixed node approximation. The Jastrow term of the wave function we consider in this work has two different kinds. Depends on the value of the scatter length. For positive scatter length, we consider this first form, and for negative scatter lengths, we consider the second form. The main difference between them is the presence of this exponential term that allows the formation of bond pairs of particles in the limit of the BEC regime. The constants A and B are chosen such that the Jastrow term goes to 1 in the range. T is a range of the Jastrow term, optimized to give the lowest energy in the variational calculation. The parameter lambda is set in a way to guarantee the continuity of the wave function by making the first derivative of the Jastrow term equals 0 in the range. Well, the simulation begins with a called variational Monte Carlo, where the energy of the system is calculated as a expected value of the Hamiltonian, calculated with the trial wave function psi t. By sampling a set of configurations distributed in accordance with the probability density obtained for psi t squared, the energy is estimated through the average of the local energy, EL. We can find some troubles in this part of the calculation because there are divergences in the wave function and in the energy when the distance between two particles with different spins goes to 0. To solve this trouble, we insert another trial move in the standard metropolis algorithms. We include the interchange of position of the closest pair of unlike spin particle. Then, after the standard metropolis trial move, we find the closest unlike spin pair and interchange the position of them. We accept this movie with the heat bath probability for the interchange, P, calculated like psi t squared of the interchanged configuration over psi t squared of the original configuration plus psi t squared of the interchanged configuration. In this way, the local energy becomes this expression. After the variational Monte Carlo calculation, we can run the called diffusion Monte Carlo calculation, where the Schrödinger equation is written as a diffusion equation like this, where tau is an imaginary time and E0 is the ground state of the system. Then we can evolve this equation. We can evolve the wave function in imaginary time, and in the limit of the very big time, we can find the exact ground state of the system. We can write the propagating equation like this integral, where g is a Green's function defined in a small time, delta tau. And psi t is used in this level of calculation as a guide function. Well, we can rewrite the propagator multiplying the term inside the integral by g0 and divided by g0, where g0 is a propagator of free particles with a drifted term, like this. Then we can take a set of configurations from the variational calculations and evolve each configuration, drifting the particles like g0 and using this exponential term to the branching process in the diffusion Monte Carlo calculation. The DMC energy is calculated through the mixed decimation like this. Okay, the results. In the first figure, we can see the energy per particle in the two different levels of calculation. The red squares are the VMC energy per particle as a function of 1 over the scatter length. In the inset, we show the results around the unitary limit. And the line is the fitting of the equation of state. The equation of state, in this case, is considered like this expression, where EFT is the free Fermi gas energy. This first term is the burst per meter, and the other terms are constants. Our fit gives the burst per meter equals 0.392, in very good agreement with several results in the literature. The contact parameter in the unitary limit can be obtained with this second constant, and our result gives 0.1101. It's very convenient to report the contact parameter per unit of volume to make a comparison of experimental data. Our result is 3.26, in very good agreement with experimental results obtained via Bragg spectroscopy, 3.06, and radio frequency spectroscopy, 2.9. Okay, now we can see the energy per particle minus the binding energy as a function of 1 over the scatter length. The binding energy is equal to 0 for negative scatter lengths. And the green solid line is the difference of energies obtained from the equation of states of the gas formed by pairs of unlike spin particles in BEC limit. The black line is the results of BCS mean field theory. Then we can see a very good agreement between our results and other theoretical calculation in the two different limits. When we have the presence of the pairs of the bound pairs of particles here and the presence of pair of Coopers. Well, In this graph, we can see the unlike spin pairs distribution function as a function of the distance for different values of the scattering length. The lines are the best fits of this function. G of r considered like B0 plus B over R times 1 over I minus 2 over A. If you fit this form, we can obtain the contact parameter through this term, B. If you use the Wigner-Bethe-Pierce boundary condition, it's possible to show the G of R is an expression like this, and where A is a constant related with the contact parameter. Then, the contact parameter per unit of volume can be obtained through this B parameter like this. And finally, we can see the contact parameter per unit of volume as a function of 1 over the scattering length. The variational results, the diffusion Monte Carlo results, the green triangles, and the extrapolated results like the blue squares. We can see a very good agreement between our extrapolated results and the experimental results. Show it like this empty square obtained using Bragg spectroscopy. And then we performed Monte Carlo simulations of an unpolarized ultracold fermi gas interacted with a contact interaction with finite scattering lengths. The Wigner-Bethe-Pierce boundary condition is considered in the calculations. Since we have a zero-range potential calculations, our results are free from any bias arising from extrapolations of potential to the zero-range limit. Here we don't have a specific potential model like Post-Teller potential or Scalar-Well potential, very common, used in the literature. Our variational wave function gives a better description of the system in the BCS region, and the contact parameter as a function of the scattering length are in very good agreement with experimental results obtained via Bragg spectroscopy. Thank you for the attention. Thanks for Brazilian agencies and the collaborators.
Yeah, thank you very much for your nice talk. We have a couple of minutes for